So in this video, we will talk about types of functional dependencies and Armstrong axioms, or you can say properties of functional dependency, right? I have already discussed what is functional dependency, how to find out or how to derive a functional dependency from a you can say given relation, or how to find out the something which is given is functional dependency or not, right? In the previous video, so you can check out that video in the side button. Now we will see the types of functional dependencies. Now mainly 4 types of functional dependencies are there: trivial, non-trivial, multi-valued and transitive functional dependency. But here I will discuss only trivial and non-trivial, because see, if I say simply functional dependency, it means single valued functional dependency. When you will got about this single valued functional dependency in deep, then it is better to teach multi-valued functional dependency. Right now I think it's not a right time to teach what is multi-valued functional dependency, right? We will discuss it later. Transitive also we will discuss later. Now for this video, right now I will discuss only trivial and non-trivial, right? Now what is trivial functional dependency? What is functional dependency? See, when I write down this is a functional dependency, means x is determinant, y is dependent, x determines y. So here the condition is what? If t1 dot x equal to t2 dot x, then t1 dot y must be equal to t2 dot y. If this condition is true and in any two tuples x value is same, then for those tuples y value must be same. If this condition is not true, then we don't care about this condition. This condition may be true or may not be true, right? Now see, what is trivial functional dependency? See, x determines y. Here if y is subset of x, then it means we can write x determines y, and this would be a trivial functional dependency. So here this y is subset of x, or you can write down if I am writing x determines x, this is also a trivial functional dependency, right? If I tell you the roll number of a student and I am asking you tell me the roll number of a student, see, from a table only I am telling you roll number of a student and asking you roll number of a student. Obviously then roll number can determine itself, right? Obviously name can determine itself, fine. So an attribute can determine itself. So this is what trivial functional dependency, right? Or you can say here this is also a trivial functional dependency if this y is subset of x, right? See, for example, here I am taking roll number determines roll number. This is all a trivial functional dependency, right? And roll number name determines name. See here, this is y, this complete is x. Now this y is subset of x. In y I have only one attribute, that is name, and that attribute is present in this set, that is here. So y is subset of x, it means this is also a trivial functional dependency. Obviously if I tell you the roll number and name of a student and I am asking you tell me the name of that student, then without looking at that table you can tell me the name, because I myself told you the name of the student, right? That is why, this is the reason that this trivial functional dependencies are always valid. No need to check it is valid or not. Trivial functional dependency will always be valid, right? Here if I say roll number and name determines roll number, that is also trivial functional dependency, right? And that is always valid. No need to check the table. Valid or invalid, that thing we will discuss, that thing we will check for non-trivial functional dependencies, right? Here if I say name and marks determines marks, that is also trivial functional dependency. If I say name determines name, that is also trivial functional dependency. Marks determine marks, definitely that would be valid, right? Department determine department, obviously that is functional dependency, but that is trivial functional dependency, right? And no need to write down these type of functional dependencies, because these are of no use. We know because that roll number can determine itself, obviously that is an obvious thing. So no need to write down these functional dependency, but these are always valid. Now what is non-trivial? See, in this case x determines y, but x intersection y is equal to phi. There would be nothing common in x and y, that is non-trivial functional dependency, right? Like if I say here roll number determines name, this is x, this is y. If you take the intersection of this and this, nothing is common, so this is what? Non-trivial functional dependency. And here I am not sure that this functional dependency is valid or not, so it may be valid, may not be valid, right? So we have to look at the table to check this functional dependency is valid or not. But this kind of functional dependency, trivial, will always be valid, no need to check the table, right? Somewhere it is also written that here in this case x determines y and y is not a subset of x. That is also non-trivial functional dependency, but this is actually semi-trivial, you can say, and this is fully trivial functional dependency, right? In this case, in between x and y we don't have anything common. See, what about semi-trivial? If I write down roll number and name determines name and marks, so here this is x, this is y. Now here y is subset of x? No, because in y I have name and marks, right? But these two are not the members of x, only name is there in x, so this is not subset of x. But x intersection y, this is not phi, because here we have name common, right? So this case you can say this is semi-trivial functional dependency. So there is non-trivial type of functional dependency, may be valid, may not be valid. You need to check the table for this to confirm this, and trivial functional dependencies are always valid, right? So these two we will discuss later. Now we will discuss what are the Armstrong axioms, or you can say the inference rules. So these rules are given by Armstrong, that is why they are known as Armstrong's axioms, or you can say inference rules, right? Using these rules you can determine, you can find out all the functional dependencies exist on a given relation or a table, right? Now how you will determine, how you will find out all the functional dependencies, that thing you will automatically come to know when we will discuss the rules with the help of this example, right? Mainly 6 or 7 rules are there, 3 are primary rules and 4 are secondary rules, right? So first one is reflexivity. Now what is this rule? See, x determines x, means any attribute or set of attribute will determine itself, right? Or you can say x determines y, here y is subset of x. This is what reflexivity rules, or this is right now we have discussed, this is also a trivial property, right? Trivial dependency you can say, right? So here in any, if you are given this table and if you are asked the functional dependencies, then definitely the functional dependencies, 5 functional dependency would be roll number determines roll number, name determines name, marks determine marks, department determines department, and course determines course, right? Means x determines y. This would definitely be the functional dependency, right? Or you can say roll number name determines roll number, name determines name. That would definitely be part of functional dependency on this table, but obviously no need to write down these kind of functional dependencies, right? These are trivial. So we know that these are always valid, these are always hold on this relation, right? Now next rule is transitivity. So what is this rule? If I ask you this thing, then many of you will say that x determines y, y determines z, then x determines z, right? Fine. Or maybe simply you will say x determines y, y determines z, and x determines z. This is transitivity rule, right? But here this one word is very important here. If x determines y and y determines z, then x determines z. If these two conditions are there, right, these two functional dependencies are there on the table, then without checking, without seeing on the table, you can say definitely x will determine z. No need to check the table. But if these conditions or any one of this functional dependency is not there in the table, then we cannot say that x determines z or not. Maybe x can determine z or x cannot determine z. In that case, we are not sure about this thing. But if this is true, then definitely this would be true. Then this functional dependency would exist on the table, definitely, right? Like if I say Ram is sibling of Shyam and Shyam is sibling of Mohan, then from here what you can conclude, what you can derive, right? See, inference or infer means what? To conclude something from given evidence. So we have these two evidence, and what you can conclude from these evidence. Ram is sibling of Shyam, means you can say brother of this Shyam, right? Shyam is sibling of Mohan. Sibling means both are having same parent. Shyam and Mohan is also having same parent. It means, can I say definitely Ram is sibling of Mohan? Yes, sure. That would definitely be true. But if I say Ram is sibling of Shyam and I don't know about that Shyam is sibling of Mohan, this I don't know. In that case, I cannot say that Ram is sibling of Mohan. Maybe it is true or may not be true, right? But if these are two conditions are true, then definitely you can say this thing. The same rule, if these functional dependencies are there in this table, then without checking on the table, you can say this functional dependency would definitely be on this table, and this is very important. When we will discuss the normal forms, in that case, you will come to know that this property, this rule is very important, right? So you must take care about this transitivity rule. See, from this table you can take one example. Name determines marks. This functional dependency exists in this table, and marks determines department. This also exists in this table. You can check because I have already told you how to check this thing in the previous video, right? Now, from here, if I ask you that is this functional dependency exists, name determines department, then without checking on this table, you can say yes, this functional dependency would also be a part of that set of functional dependencies, right? So from these, I can derive this thing. That is why I told you that using these rules, you can find out all the functional dependencies on a relational database. Let us take this example. I have added one more record in this table. Now see, here check. This dependency exists, name determines marks. Yes, this exists here, right? Here, see now, marks determines department. This functional dependency is not there. This is not a functional dependency in this table. Marks, department. See, here 80 and 80 are repeating, but this is x, so y value in the same tuple y value should be same, but here we have IT, here we have EC. So this functional dependency does not exist on this database, right? Now see, we cannot say that if this does not exist, then this is not true. Then name cannot determine department according to the transitivity rule. No, if this is not true, then we cannot say anything about x to z. You can check name to department. Name determines department. See, here A and A same, but the y value is also same. B and B same, this value is also same, and we don't have any repeating value, right? So this functional dependencies still exist on this table. So this is actually the transitivity property. If this and this is true, then definitely this functional dependency would be there, right? If this functional dependency is there, maybe any one of this is not there, then we cannot say that this is also not true. It may or may not be true, we can't say, right? Now next is augmentation. See, augmentation means in general English or in meaning of augmentation means what? Make something bigger or lengthy by adding something to it, right? Now what is this augmentation property in this case? See, if x determines y, and here see these x and y may be set of attributes, maybe one attribute or set of attributes, right? If x determines y, this is a functional dependency, this functional dependency exists on a table, then you can add any attribute both side. If you are adding a, it means you can add a here, xa will determine ya, right? This would always be true. Like in this case, suppose I am saying roll number determines marks, right? This functional dependency exists here. Fine. Now you can add roll number marks determines name, and here also same attribute, marks and marks both side. So this would definitely be true. This would definitely be a functional dependency on the table. Without checking on the table, you can say this functional dependency will exist, right? According to augmentation rule. See, if this is true, then only this is true, right? But I cannot say that if this is false, then this also false. It may or may not be true, right? We are concerned about if this is true, then this must hold. If in my class I can determine each student by roll number, right? If I say roll number 15, tell me your name. So roll number 15 and name is this one, right? If I say roll number 15 with marks 78, tell me your name and marks. So marks already I have told, right? And roll number can determine name, that already exists. So definitely he or she can tell me the name and marks, right? So this is augmentation property. We are making it bigger by adding something new, that is marks I have added on both sides. Same attribute you need to add on same both sides. Now see, one frequently question asked is what? If x determines y, then x must be a primary key. No, that is not a case. It's not like that only primary key can determine any other attribute, right? Here name determine marks, this functional dependency exists, but here you can see that name is not a primary key. Fine. So that is not a condition, that necessary condition that the x should be a primary key, right? Now next is, these three are primary rules. With the help of these rules we can determine all the functional dependencies, right? But to make it simple, right, we have some secondary rules as well. See, those secondary rules also we can prove using these rules, right? Like in DE, NAND and NOR gates are universal gates. All the other gates we can determine from NAND and NOR, but still we have AND, OR, XOR, many gates we have to make the process simple, right? That is why we have some secondary rule as well. So those are, first is union. According to this rule, if x determines y and x determines z, see here in this functional dependency, in this functional dependency, determinant is same, only dependent is different. Then you can say x determines both y, z. You can write down these two at one place, right? If I say in this case roll number determines name and roll number determines marks, can I write roll number determines name comma marks? Obviously I can write this thing, right? So this is what union rule. If this is given and this is given, then definitely without checking on the that table you can write x determines y, z. Next is decomposition or splitting property. Now what is this property? See, if x determines y, z, then how you can write x determines y and x determines z. Splitting, or you can say decomposing, you are splitting this thing yz. X determines yz, right? This is complete one unit. So now you can write down x determines y and x determines z. You have splitted this dependent. But see, this is not true. If I write if xy determines z, then you can't write x determines z and y determines z. No. you cannot split the left hand side, you cannot split the determinant, right? If I say both name and marks determines department, right? But here I can't say that individual name also determines department, individual marks also will determine department, right? So you can split only the right hand side, the dependent side, you cannot split the determinant side. This is also very important point to note here. And here see, it's not like that it is x, so it is single attribute. This x, y, z, these are what? Set of attributes. See, let us take this example. Suppose I am taking here name and marks determining department and course. Suppose this is true in this case, this functional dependency exists in this table, right? So now using this rule, without checking the table, what you can write? You can write name, marks determine department and name, marks also determine course. You can split these, but we cannot split these, right? Maybe in this table it is true that name only determines department course, marks only determine department course, but it is not a rule. We cannot take it as a rule. It is not always true, but this thing, splitting of right side, will always be true on a relation, on a table, right? So next rule is what? Pseudo transitivity. So what is this pseudo transitivity rule? See, here you can write if x determines y and y z determines a. Suppose these are true, these two functional dependencies are there on a given table, then definitely you can say x z will determine a. See here what we have done, we know that x will determine y and both y and z, combination of these two will determine a, another set of attribute. Then you can say here, see, z is there as it is, but y is what? Using x we can determine y, so at the place of y you can write down x. So here you can say x z will determine a, right? See, let us take, if I say roll number determines name, right, on this table it holds, and name and marks both will determine department. So now can you say that roll number and marks will also determine department? Yes, because if I say that I'm in my class, if I say roll number 15, tell me your name, and I assume that roll number is different, means using roll number I can determine each student, that is for sure. So now, and then I say name of that student, that Nisha, 78 marks are suppose 78, and using that I can determine the department of that girl. So now can I say that using the roll number, means roll number 15, suppose roll number of Nisha is 15, roll number 15 marks 78, and using that I can determine the department definitely, because at the place of name I can definitely write down roll number, because using roll number I can determine name, right? So you can replace here name with roll number, fine. And next rule is composition. This rule says if x determines y and a determines b, then definitely you can write x a determines y b. You can compose these things. X determines y means suppose roll number determines name. Second is suppose marks department determines course, right? So what you can write, you can combine determinant of this FD and this FD, functional dependency, both functional dependency, right? Means roll number, marks, department will determine, you can combine this and this, dependent of both functional dependency, name and course, right? This would definitely be true according to Armstrong axioms, right? See, these rules are very important because we are going to use these rules further when we will discuss normalization, right? When in that case, obviously you need to find out some keys also, attribute closure as well. At that time you need these kind of rules, right? So these rules are very important. So now in next video I'll discuss what is attribute closure, or how to find out closure set of an attribute, right? And at that point of time you need these rules. Without these rules we cannot find out attribute closure, and attribute closure is very important topic for the point of view of normalization, right? So now I'll see you in the next video. Till then, bye bye, take care.